Last time when we stopped, we were looking at the one dimensional unsteady state problem in an infinite slab. The situation was as follows: you have an infinite slab of width 2b, initially at a temperature T0. It is suddenly immersed in surroundings at a temperature Tf. T0 may be greater than Tf or less than Tf. If T0 is greater than Tf, the slab will cool. If T0 is less than Tf, the slab will heat up. There is a heat transfer coefficient H on the two faces of the slab. It is a symmetrical situation about the center line of the slab. So, we were looking at that problem, which is a one dimensional problem in x and in time, unsteady state problem in x and time. We put down the differential equation, we put down the boundary conditions on the two faces x equal to b, x equal to minus b, and we stated the initial condition. And then I did not solve the solution, the differential equation. I said the solution can be obtained by a method called the separation of variables method, and the solution, after doing the separation of variables method, the solution is obtained in the form of a convergent series, which I showed you. This is the solution that I showed you last time, where lambda 1, lambda 2, lambda n are called the eigenvalues of the problem. And I told you that they are the roots of the equation cotangent lambda b is equal to lambda k by h, which is equal to lambda b divided by h b by k. And then graphically I showed you how the values of lambda 1, lambda 2, lambda 3 etcetera can be obtained graphically by intersecting the cotangent graph with the straight line graph obtained for the right hand side. The cotangent graph is on the left hand side, the straight line lambda b divided by h b by k is on the right hand side. The intersection of the two of this line with the cotangent curves gives me the infinite solutions lambda 1, lambda 2 etcetera. Use those solutions in the convergent series and we get the temperature distribution theta by theta naught. This is where we stopped last time. Now, the solution which I showed you can also be expressed in dimensionless form as shown. This is the solution, the same solution in dimensionless form, theta by theta naught, the left hand side is the same, is equal to 2 times the summation n equal to 1 by infinity sin lambda n b divided by lambda n b plus sin lambda n b cosine lambda n b, that is the same as earlier, multiplied by e to the power of minus lambda n b squared multiplied by alpha t by b squared. You notice I have brought in the two dimensionless numbers in the exponent of e, and then I have written the cosine as cosine of lambda n b into x by b. So, what we now have is a situation in which the dimensionless temperature on the left hand side theta by theta naught is a function of the lambdas, lambda b's rather. So, function of lambda n b, lambda 1 b, lambda 2 b etcetera. It is a function of this dimensionless number alpha t by b squared, which appears in the exponent of e, and it is a function of x by b, which is the location of the point where we want the temperature inside the slab. X by b tells me a location, x by b can vary from 0 to 1. When x by b is 0, we are talking of the center line of the slab. When x by b is equal to 1, we are talking of the face of the slab, right. So, this method of representation shows us that theta by theta 0 is a function of lambdas, lambda b's, alpha t by b squared and x by b. Now, from the method that I showed you for obtaining the lambda b's, you know very well that the lambda b's depend on h b by k. It is nothing but the intersection of the cotangent curves with the straight line that I get on the right hand side of that equation for solving for the lambda b's. So, the lambda b's really depend on h b by k, and therefore, I can say theta by theta 0 is also a function of h b by k, alpha t by b squared and x by b. The dimensionless, or in words, the dimensionless temperature on the left hand side, the dimensionless temperature of any point in the slab theta by theta naught, which can vary from 0 to 1, is a function of 3 dimensionless numbers h b by k, alpha t by b squared and x by b. Now, let us look at the significance of these 3 numbers. Just let me talk a little about the significance of these numbers. The first number h b by k is called the Biot number. It is nothing but the ratio of the thermal resistance of the solid to the thermal resistance at the surface. That is all that it is. That means, if the Biot number is less, the thermal resistance inside the solid is small compared to the thermal resistance at the surface. Biot number tending to 0 is a situation of negligible internal temperature gradients. All right. So, as Biot number increases, the thermal resistance inside the solid becomes important and we cannot neglect internal temperature gradients. That is what Biot number is. It is a ratio of 2 thermal resistances, the ratio of the thermal resistance of the solid to the thermal resistance at the surface, the 1 upon H A at the surface. The second dimensionless number alpha t by b squared is called the Fourier number. It is a dimensionless measure of time, because time is appearing in the numerator. So, the larger the time, the larger the Fourier number. And the third number, which I said a moment ago, is a dimensionless measure of location in the slab. X by b can vary from 0 to 1, x by b equal to 0 is at the center line, x by b equal to 1 is at the surface of the slab. So, effectively, once I specify these 3 numbers for a particular situation, particular slab and a particular situation, I can get a value of theta by theta 0 from the solution which I have shown you just a moment ago. Now, this solution has been obtained numerically and is often presented in graphical form in 2 charts as follows. The theta by theta 0, which is the left hand side of the solution, is split up into 2 quantities, theta at x by b equal to 0 upon theta 0 into theta divided by theta at x by b equal to 0. Theta at x by b equal to 0 is the theta on the center line and theta 0 is the initial difference of temperature T 0 minus T f. Theta is the temperature at any point in the slab at any time minus T f. All right. So, we are splitting up this theta by theta 0 into these 2 quantities, the product of which gives me theta by theta 0, and the graphical representation is as follows. The graphical representation is as follows. Now, let me show it to you. On the x axis, I have alpha t by b squared. I have already told you the dimensionless temperature is a function of 3 parameters. What is it? The Fourier number, which I am plotting on the x axis, alpha t by b squared. Let me write it in bigger letters here, alpha t by b squared. All right. Then the location in the slab x by b is a parameter against which we also measure. In this case, we want the temperature only at the center. So, it is theta, let me write this again in big letters, theta at x by b equal to 0 divided by theta 0, theta naught, and the parameter varying from graph to graph, which is drawn here, is the inverse of the Biot number. What we have here is k by h b, k by h b, k by h b is nothing but 1 upon h b by k, which is the inverse of the Biot number. So, the inverse of the Biot number is the parameter varying from graph from each line which is drawn on this chart. All right. So, now suppose I want the temperature at the center line of the slab at any given time. Suppose I have a slab, I want the temperature at the center of the slab at any given time. I know I have the data of the slab, its dimensions, the values of alpha, that is the thermal diffusivity of the slab, etc. What will I do? If I want the temperature at any given time, I calculate the Fourier number. All right. I know I am given the heat transfer coefficient at the surface, I know half the width of the slab, I know the thermal conductivity of the slab, calculate H b by k, and therefore 1 upon H b by k. So, given for the given time, calculate alpha t by b squared, you got your value of alpha t by b squared, go up vertically to the value of 1 upon the Biot number, the inverse of the Biot number, then go horizontally and you will get the value of theta at x by b equal to 0 upon theta naught. From this you can calculate the value of theta at x by b equal to naught, and therefore, t at x by b equal to naught, that is at the center line. This is how you would proceed to use this chart to get the temperature at the center line at any given time for a given slab with given characteristics of properties and width, etc. The second chart which we use, this is the chart for giving the temperature at the center line. The second chart is for connecting with the temperature at any point in the slab. We do not want just the temperature at the center, we want the temperature at any point in the slab. So, the second chart gives me theta at divided by theta at x by b equal to naught. Let me again write that in big letters, theta divided by theta at x by b equal to naught, that is at the center line, and this is on the y axis, and on the x axis I have x by b, again let me write it in big letters, x by b, which is x by b equal to 0 is the center line, x by b equal to 1 is the face of the slab. So, suppose I want the ratio of the temperature at any point in the slab to the temperature at the center line, okay. Then I will first get the value of x by b, it will vary from 0 to 1, whatever it is. I will go up vertically, go to the value of 1 upon the Biot number. This particular quantity here is again the same thing that I mentioned earlier. It is 1 upon H b by k, 1 upon the inverse of the Biot number. So, calculate this. So, given a particular location in the slab, whatever is the value, go up to the particular value of 1 upon H b by k, then go horizontally and you will get the ratio theta divided by theta at x by b equal to 0. Now, from the previous chart you have got theta at x by b equal to 0. So, if you multiply the value obtained from the previous chart with the value obtained from this chart, you will get the value of theta. So, this is how we use the two charts. The first chart for getting the temperature at the center line, the second chart for getting the ratio of the temperature at any point in the slab to the temperature at the center line. We will illustrate these ideas by doing a numerical problem in a short while. So, that these ideas will get properly illustrated. I will do a numerical. All right. Now, let me just for a moment diversify and say a very similar problem can be to that of the infinite slab can also be posed for a long solid cylinder and for a solid sphere. An identical problem can be solved. For the long solid cylinder, we will say we have a long solid cylinder of radius capital R. It is initially at a temperature T 0. It is suddenly immersed in surroundings which are at a temperature T f, and there is a heat transfer coefficient H at the circular face of the cylinder, all along the circular face of the cylinder. Find the temperature inside this cylinder at any point in the cylinder as a function of time and of course, space, that is function of r and t. We can put down a differential equation using our general differential equation in cylindrical coordinates. We can put down a boundary condition, we can put down initial condition and solve it. The solution more or less proceeds along similar lines to what we had for the infinite slab. You get a separation of variables technique and solve it, and similarly for a sphere. So, analogous problems to those for the infinite slab have also been solved for the cylinder, the long solid cylinder and the sphere, and the results are presented graphically as theta by theta naught equal to theta at r by r equal to 0 upon theta naught. This is the temperature in the case of the cylinder, this is the temperature on the axis of the cylinder, into theta upon theta at r by r equal to naught. So, you see for the slab we had x by b equal to 0, now for the cylinder we had r by r equal to naught. If it is the sphere, this would be the center of the sphere, r by r equal to naught. Okay. So, if the problems of the slab, the cylinder and the sphere are all similar. We have talked in detail about the problem of the slab, but identical problems can be set up for the cylinder, long solid cylinder and the sphere. They have been solved, series solutions are available, and like the slab, we have the solution available in the form of 2 charts for the cylinder and 2 charts for the sphere. The only difference is, instead of b being the characteristic dimension in the Fourier number or in the Biot number, we now have capital R, which is the radius of the cylinder or the radius of the sphere, as the characteristic dimension. That is the only difference. Okay. So, whatever we say for the slab has also been done for the cylinder and sphere. Solutions are available in the form of an infinite series and also in the form of charts. Now, let us illustrate these ideas with the help of a numerical problem. We will do a numerical problem for an infinite slab. Let me say, I am going to do a numerical problem now. Let us say the problem is as follows. We have an infinite slab. Let me draw one. We have an infinite slab of width. We have an infinite slab of width 1 centimeter, whose width is 1 centimeter. All right. It is initially at a temperature, let me draw the temperature distribution initially. It is initially at a temperature of 200 degrees centigrade. So, let us say this is the 0 line for temperature, and initially it is at a temperature of 200 degrees centigrade, uniform temperature of 200 degrees centigrade. So, T 0 equal to 200 degrees centigrade. Suddenly, this slab is put into surroundings, which is the surrounding temperature is 20. So, let me draw 20 here. Let us say this is T f equal to 20. Surroundings are at 20 degrees centigrade. So, the slab is going to cool, and with time, if it is immersed, and we are going to get temperature distributions like this, etc. Eventually, if you wait long enough, at time t equal to infinity, the temperature distribution in the slab will be tending almost to T f, to the value of T f, that is 20 degrees centigrade. So, with time, the temperature is going to, temperature distribution inside the slab is going to change like this. Now, we would like to find the temperature in the slab after a time t equal to 5 minutes. Let us say this corresponds, this temperature distribution corresponds to t equal to 5 minutes. You are asked to find the temperature in the center of the slab after t equal to 5 minutes, and you are asked to find the temperature at the face of the slab after t equal to 5 minutes. These are the 2 points which I have marked as a circle. You are asked to find t at x equal to 0 and after 5 minutes at t equal to 5 minutes. We want to know t at x is equal to 0 and we want to know t at x is equal to b. These are the two values we want. All right. We want to use the charts. We are given the properties, of course, are needed. So, we are told that rho, the properties are as follows. Rho is equal to 2200 kilograms per meter cubed. Cp is equal to 1050 joules per kilogram Kelvin specific heat, and the thermal conductivity K is equal to 0.4 watts per meter Kelvin. These are the values given, property values given. You are also told that the heat transfer coefficient H at the surface is 150. The value of H is equal to 150 in the usual units, watts per meter squared Kelvin. Find the temperature at the 2 points, that is at the center line, at the center plane and at the face after 5 minutes have elapsed. That is the problem. It is a straightforward problem in which we want to make use of the charts, nothing else. Okay. Now, first of all, what is theta 0? Theta 0 is equal to T 0 minus T f, it is equal to 200 minus 20 equal to 180 degrees centigrade. Biot number Bi is equal to Hb by K, which is equal to H is 150 watts per meter squared Kelvin. B is equal to half a centimeter, B is half the width of the slab, half a centimeter. So, it will be 0.005 meters divided by K, which is 0.4. So, the value of Bi comes out to be 1.875 and 1 by Bi, the inverse is what we need, will come out to be 0.533. Okay. Now, let us go to the next part. We need the Fourier number. The Fourier number will be given by Fourier number will be equal to alpha t by b squared, which is equal to alpha is k by rho Cp. So, alpha is k by rho is 2200 into Cp is 1050. So, that is alpha multiplied by the time in seconds, which will be 5 minutes is 300 seconds, and b squared is 0.005 the whole squared, which comes out to be, the Fourier number comes out to be 2.0779. Now, we go to the charts. All right. So, we will go to the first chart, which I showed you a moment ago. Let me just show it again. The first chart gives the temperature at the center line. So, let us look at that. Our Fourier number is 2.07, all right, which is somewhere here on the chart, 2.07. 1 upon the Biot number is 0.5. So, if you go up like this vertically and this is 0.5 here, if you go up vertically, you will go somewhere here roughly. Okay. One can do it more exactly, and one has to take account of the fact that this is a logarithmic scale on the y axis and the x axis and so on. But if you will come somewhere at this point, which is about 0.12, that is what I am reading it. So, theta at x by b equal to 0 upon theta naught from the first chart is 0.12. So, let us write down that from the chart the first chart gives me theta at x by b equal to 0 divided by theta naught, okay, corresponding to the value of the Fourier number and the 1 upon the Biot number. The first chart gives me about 0.12. All right. The second chart gives me the ratio of the temperature at any point to the temperature at the center line. This is the second chart now. X by b, we want the temperature at x by b equal to 1. So, we are going to go on this line x by b equal to 1, go up till you get 1 upon h b by k equal to 0.533, which is approximately somewhere here. Go horizontally and you will get theta divided by theta at x by b equal to naught equal to 0.48. Theta divided by theta at x by b equal to naught equal to 0.48. So, these are the two values which we got for this problem from the charts. Now, we want the temperature. So, let us get the temperature from the first value. We get theta by x by b equal to naught is equal to 0.12 into theta naught, which is 180, and that gives us 21.6 degrees centigrade. Therefore, T at x by b equal to naught equal to 21.6 plus 20, which is equal to 41.6 degrees centigrade. So, this is the first value that we are looking for, and the second one that we are looking for is theta at x by b is equal to 1 is equal to 0.48 multiplied by theta at x by b equal to naught, that is 21.6. So, that comes out to be 10.4. Therefore, T at x by b equal to naught is equal to T at x by b equal to 1, not x by b equal to naught. T at x by b equal to 1 is equal to 10.4 plus 20, which is equal to 30.4 degrees centigrade. So, this is the second value that we get, the second number that we are looking for from the charts. So, you see how to use the charts. For a given situation, calculate the Fourier number, calculate 1 upon the Biot number, use the first chart to get the temperature at the center line, use the second chart to get the ratio of the temperature at any point to the temperature at the center line. Once you have done that, you have got the temperature at any point inside the slab at any given specified time. That is what the charts are for. One could also use the charts in the reverse manner. One could ask the question, how much time does it take for a particular point in the slab to reach a particular temperature? That is the reverse problem, you understand. In which case, what we are saying is the value on the y axis is known, you need the value on the x axis, that is, you need to find out the Fourier number. Now, try doing that on your own, it is not very difficult, you will have to think a little. Try doing the reverse problem, that is, for a given slab, given properties, a given situation, find the time taken for a particular point in the slab to reach a given temperature during the cooling process. I want you to do that type of problem on your own. All right. Now, I talked about the significance of the Biot number. Let me again come back to it. The value of the Biot number decides whether internal temperature gradients are important. I have said that to you earlier. As the Biot number tends to 0, internal temperature gradients are negligible. But where? As an engineer, we must have some criterion. There is no such thing as a 0 Biot number, because that would require a situation which is absolutely ideal, a k equal to infinity, which does not exist. The usual criterion as engineers which we use is that if the Biot number is less than 0.1, we neglect internal temperature gradients. We find that then temperature gradients are small enough that we can neglect them. For a slab, therefore, what we are saying is H b by k is less than 0.1. For a cylinder or a sphere, what we are saying is H r by k is less than 0.1. You understand? That is how we are putting down the criterion. 0.1 is somewhat arbitrary. It has been picked by people based on a look at the solutions in the charts. That is, from Biot number 0 to 0.1, if you consider the changes in temperatures across the whole slab or across the whole cylinder, they are small enough not to worry about for most situations. So, this is a criterion that we often use. We calculate the Biot number based on the characteristic dimension of the body, and if that Biot number is 0.1 or less, we say we will neglect internal temperature gradients and use the simpler solution which I got for you earlier. If not, then we must obviously have a more detailed solution of the partial differential equation. All right. Now, what about some other shapes? Suppose I take some shapes and ask what will happen, what do you do with them? For other shapes means shapes other than an infinite slab or an infinite cylinder or a sphere. For other shapes, the criterion that we use is H L by k must be less than 0.1, where L is the characteristic dimension of the solid body. Is the characteristic dimension. L is a measure of the distance, the maximum distance that heat has to flow within the body. Why is it? So, therefore, for a slab it is half the width, because heat flows from the center line outwards towards the two faces. For the cylinder, why is it the radius? Because from the center axis heat is flowing outwards towards the faces, or inwards from, if the body is heating up, inwards from the circular face towards the center line. You understand? Now, suppose I have some other shape. Let us take an example. Let me take a shape which is a structural shape, which we use so often in practice. I am going to draw here an angle, a shape which is used in so much structural work. All right. Let us say I have an angle iron like this. All right. Its width is, its thickness rather, is T, all right, in this direction. This direction also it's T, like this, and it is a long angle iron like this, and in this direction the width is B, let us say like this. It is B like this direction. B in this direction. It's an angle iron, B and B are the legs and T is the thickness of the angle. It's a long angle iron. What will I take as the characteristic dimension? If this is going through some transient heat conduction process and I want to know whether to neglect internal temperature gradients or not neglect internal temperature gradients. Well, ask yourself now, how will heat flow if this angle iron is going through a cooling process? If you ask yourself that question, you will see that the heat from this angle iron will primarily flow like this. These are the dominating phases through which heat is flowing, like this, isn't it? If it is undergoing an unsteady state, like this or like this. So, the distance which the heat flows will be half the thickness T, and therefore, the characteristic dimension which I should take for an angle iron would be T divided by 2. That would be the characteristic dimension to take. If I use this characteristic dimension and if I find that the Biot number is less than 0.1, well, then I would neglect internal temperature gradients. Okay. Now, let us move on a little and do one more numerical problem. The problem I am going to do is the following now. We are given a hollow metal sphere. Let me draw that for you. We are given a hollow metal sphere all right, like this, a hollow metal sphere 10 centimeters in diameter OD and 5 centimeters ID. Its inner diameter, it is a hollow sphere, this is 5 centimeters. And the OD is 10 centimeters. It is a solid sphere, but hollow in the middle. Initially at a temperature T0, initially at a temperature of 500 degrees centigrade. Suddenly it is cooled in an oil bath. That oil bath is at a temperature Tf equal to 40 degrees centigrade. Cooled in an oil bath at a temperature of 40, and the surface heat transfer coefficient is 90 watts per meter squared Kelvin. So, the value of H at this outer surface is 90 watts per meter squared Kelvin. You are told that there is negligible heat transfer at the inner surface. So, at this inner surface, this is the inner surface in the hollow sphere, there is negligible heat transfer, H is equal to 0, all right, no heat transfer or negligible heat transfer. So, all the heat transfer is taking place from the outer surface. The properties of the material are given. You are told that rho is equal to 8000, it is a metal, rho is 8000 kilograms per meter cubed. K, the thermal conductivity, it is a metal, is about 50 watts per meter Kelvin, and Cp is equal to 420 joules per kilogram Kelvin. All right, these are the properties of the metal. Find the temperature of the sphere after 100 seconds have elapsed. Find the temperature at any point in the sphere after 100 seconds have elapsed. At t equal to 100 seconds, capital T is equal to what? Find the temperature in the hollow sphere at any point after 100 seconds have elapsed. Now, the first thing we have to do is to find the Biot number for this metal sphere. All right. So, first let us now calculate the Biot number. The Biot number is given by, for the hollow sphere, HL by K. Now, what will we take as the characteristic dimension? You see, this is a hollow sphere, heat is flowing from inside out. The maximum distance that the heat will flow will be from here outwards, because there is no heat flow on the inner inside, in the hollow space inside. So, the maximum distance the heat is going to flow is from here to here, which is 2.5 centimeters. So, let us take L equal to 2.5 centimeters. Okay. Put that in. So, what will we get? We will get Bi is equal to H, which is 90, multiplied by the characteristic dimension 0.025, divided by the conductivity 50, and that comes out to be 0.045, which is much less than 0.1. Okay. Therefore, this is a case where we can neglect internal temperature gradients. Therefore, because of this value of Biot number, therefore, internal temperature gradients are negligible. You follow? So, we have taken a characteristic dimension, and then using that characteristic, taken a reasonable characteristic dimension, using that value we have shown that the Biot number is less than 0.1 and concluded that internal temperature gradients are negligible. Once we have arrived at that conclusion, then the problem is one of only substituting into the expression which we have derived earlier with negligible internal temperature gradients, that is theta by theta naught is equal to e to the power of minus H A T divided by rho C P V. All right. That is all we have to do. So, first let us calculate H A T by rho C P V. H A T divided by rho C P V is equal to, H is 90, A is 4 pi r squared, 4 pi the area on the outer surface 0.05 squared into the time t 100 seconds, all right, divided by rho 8000 into Cp, which is 420, multiplied by the volume of the sphere 4 by 3 pi into 0.05 cubed minus 0.025 cubed. That is the volume, and if you calculate that, you will get 0.7694. That is the value of H A T upon rho C P V. Okay. Now, let us plug into our relation. So, we get theta by theta naught is equal to e to the power of minus 0.7694, which is equal to 0.4633 Therefore, theta, or rather T, the temperature T, is equal to 0.4633 multiplied by T 0 minus T f, that is 500 minus 40 plus T f, that is 40, and that comes out to be 253.1 degrees centigrade. So, that is the answer to the problem. All right. Now, so this is the answer to the problem, because we could neglect internal temperature gradients. If for instance, in this particular case, the data were such that the Biot number were more than 0.1, and you find yourself unable to neglect internal temperature gradients, then you can formulate the problem in terms of a partial differential equation in spherical coordinates. You will get boundary conditions, you will have an initial condition, and you will have to solve that partial differential equation with those given conditions, get a series solution. It can probably be done, but it will be far more complicated than what we have done by in this method, when we have been able to neglect internal temperature gradients. Now, we have now looked at one dimensional problems, but I want to tell you also that the one dimensional unsteady state solutions that we have got are also useful for 2 and 3 dimensional unsteady state situations. 2 and 3 dimensional unsteady state heat conduction problems. We want to briefly look at such solutions. We are not going to solve the differential equations ourselves, but I am going to give you the solutions which have been obtained by others. Let us look at the following problem. Let us say I have a long rectangular bar, whose dimensions are 2a multiplied by 2b. Let us say I have a long rectangular bar, dimensions 2a by 2b, something like this. Let us say I have a cross section which is like this. Two a by 2b, okay. This is 2a, and this is 2b. A long rectangular bar whose cross section is 2a by 2b, long in the z direction, like this. Long in the z direction, like this. All right. And let us say the center line is the center of the bar, that is here. So, this is our center line. The origin of the xy coordinate axis. So, this is x, this is y. Okay. It is a long rectangular bar like this, initially at a temperature T 0, the bar is initially at T 0, immersed at time t equal to 0 in surroundings at a temperature Tf. Surface heat transfer coefficient on all faces surface heat transfer coefficient on all faces is H. Find the temperature in this rectangular bar as a function of x, y and time. That is the problem. T, the temperature in the bar will be a function of x, y and time. Vary in 2 dimensions x and y, it will also vary in time. Find the temperature distribution in this bar as a function of x, y and time. That is the problem. Now, next time we will look at this solution. We are not going to solve the problem, we are going to give you the solution which has been obtained for this situation and show how to use the charts for one dimensional situation for this 2 dimensional problem.